makes your smartphone smart, or how your computer can do so many amazing things so quickly? The answer is a tiny but incredibly powerful material called a semiconductor. Think of it like a light switch, but a very special one. Some materials, like copper wire, are conductors. Electricity flows through them easily, like water through a wide-open pipe. They are always on. Other materials, like rubber or glass, are insulators. They stop electricity completely, like a sealed cap on that pipe. They are always off. Semiconductors are the cool materials in the middle of these two extremes. A semiconductor can act like both a conductor and an insulator. That's its superpower. We can control when it lets electricity pass through and when it blocks it. By precisely switching the flow of electricity on and off in incredibly fast patterns, we can create signals. These signals are the language of computers, representing ones and zeros, or on and off. This simple idea, repeated billions of times on a tiny chip, allows devices to calculate, store information, and run all the apps and programs we use every day. The most famous semiconductor material is silicon. You might know it from its more common form, sand. That's right, the basic ingredient for the most advanced technology on Earth is found on beaches and in deserts all over the world. Now let's get into the science of it. Semiconductors come in a couple of main types. The first is called an intrinsic semiconductor. This is a semiconductor in its purest form, like a perfect crystal of silicon. In this state, it's not a very good conductor at all. It has just enough free-moving electrons to be considered a semiconductor, but not enough to be useful for complex electronics. Think of it as a blank slate, a clean canvas waiting for an artist to come and add color. To make semiconductors truly useful, we need to modify them. This brings us to the second type, extrinsic semiconductors. This is where the real fun begins. We take that pure silicon and add tiny amounts of other elements. This process is called doping. The first is called an N-type semiconductor. Here we add an element like phosphorus. Phosphorus has extra electrons to share. These extra electrons can move around freely, making the material much better at conducting electricity. The other subtype is called a P-type semiconductor. For this, we dope the silicon with an element like boron. Boron has fewer electrons than silicon. This creates holes or empty spots where an electron could be. These holes act like positive charges that can also move through the material. In a P-type semiconductor, it's the movement of these holes that allows electricity to flow. It's a different way of carrying a current, but just as effective. The real magic happens when we put these two types together. When an N-type and a P-type semiconductor are joined, they form something called a p-n junction. This junction acts as a one-way gate for electricity, allowing it to flow from the P side to the N side, but not the other way around. This simple structure is the basis for a diode, and by combining them in different ways, we can build transistors, the microscopic switches that power our entire digital world. You might not see them, but semiconductors are working for you from the moment you wake up until you go to sleep. That alarm clock that woke you up this morning, it has a semiconductor chip inside to keep time and sound the alarm. When you walked to the kitchen and turned on the coffee maker, another chip controlled the brewing temperature and time. Even your microwave uses a semiconductor brain to heat your food perfectly. These tiny chips are the unsung heroes of our modern homes. Think about your journey to school or work. If you traveled in a modern car, you were surrounded by semiconductors. The engine control unit, which manages fuel efficiency and performance, is a powerful computer. The anti-lock braking system, or ABS, that keeps you safe during a sudden stop relies on sensors and chips. Public transportation, like trains and buses, also uses complex semiconductor-based systems to manage schedules, control speeds, and ensure passenger safety. Of course, the most obvious places we find semiconductors are in our communication and entertainment devices. Your smartphone is a pocket-sized supercomputer powered by a central processing unit, or CPU, that contains billions of transistors built from semiconductors. Your television, your laptop, and your video game console all rely on these chips to process information and create the bright, colorful images we see on screen. They enable us to connect with friends, learn new things online, and explore vast digital worlds, all from the comfort of our homes. Even beyond our gadgets, semiconductors play a vital role in bigger systems. The power grid that delivers electricity to our homes is managed by semiconductor-based controls. Medical equipment in hospitals, from MRI machines to heart monitors, uses them to save lives. They are in the satellites that orbit our planet, providing weather forecasts and GPS signals. They are quite simply the invisible foundation of our technological society. Creating a semiconductor chip is one of the most precise and complex manufacturing processes in the world. It all starts with a very common material, sand. Specifically, we use quartz sand, which is rich in silicon dioxide. The first step is to heat this sand to an extremely high temperature in a furnace, over 2000 degrees Celsius, to separate the silicon from the oxygen. This gives us metallurgical-grade silicon, which is about 99% pure. But for electronics, we need it to be much purer than that. The silicon is converted into a gas, purified through distillation, and then turned back into a solid. The result is electronic-grade polysilicon, which is astonishingly pure, 99.9999999% pure. That's like finding only one wrong grain of sand in a line of a billion grains. This ultra-pure silicon is then melted down, and a tiny seed crystal is dipped into the molten pool. As the seed is slowly pulled out and rotated, the silicon cools and grows around it, forming a single, perfectly structured crystal called an ingot. These ingots can be over 2 meters long and weigh hundreds of kilograms. Once we have the perfect ingot, it's sliced into very thin, circular discs called wafers. These wafers are polished until they are incredibly flat and smooth, like a flawless mirror. Now the wafer is ready to have circuits built on it. This happens in a super clean factory called a fab, which is thousands of times cleaner than a hospital operating room. The process involves adding and removing layers of different materials in a complex pattern, a technique called photolithography. It's like a microscopic form of screen printing repeated hundreds of times. The wafer is coated with a light-sensitive material. Ultraviolet light is then shown through a mask, which acts like a stencil for the circuit design. This pattern guides where we add N-type and P-type elements, and where we etch tiny pathways for electrical current. This layering process is repeated over and over, building up billions of transistors and their connections. Finally, the wafer is cut into hundreds of individual chips, which are tested and packaged. From sand to a super chip, it's an amazing feat of science and engineering.